Chapter 15.3 introduces pH calculations. pH stands for the power of hydrogen. The equation we'll be using is pH is equal to the negative log of H3O plus concentration. So as H3O plus increases, our pH is going to decrease, and this is by a tenfold. So a tenfold increase in our H3O plus concentration decreases our pH by 1, since it is on a log scale. The pH scale itself ranges from 1 to 14, some might say 0 to 14, depending on what type of equipment you're using. Anything below 7 is acidic, 7 is neutral, and then anything above 7 is basic or alkaline. And then neutral is when your H3O plus and OH minus concentrations are going to be equal, so when your hydroniums and hydroxides are equal to one another. So when you're calculating pH for a strong acid, this one says, what's the pH of a solution with an H3O plus concentration of 1.8 times 10 to the negative fifth molar? So we're going to write out our equation. pH equals negative log of H3O plus, plug in our molarity, and that will come out to be 4.74. So this would be an acidic solution. It's below 7. This one is going in reverse. This time we're given the pH and we are asked to find the hydronium ion concentration. So for our equation, it's going to be H3O plus concentration is equal to 10 to the negative pH, or anti-log of the pH. So we do 10 to the negative 3.12 power, and that will give us 7.6 times 10 to the negative fourth molar. This piece of equipment in the picture here is called a pH meter. You put a probe in your solution and it'll give you a digital readout of what your pH value is. There's also something called pOH. Now this is actually a made-up thing. It doesn't really exist, but it is useful in helping to find the pH of bases. So since acids and bases are opposites, pH and pOH are opposites. So we have two equations we can use here. pH plus pOH equals 14, because that's as big as the pH scale gets. And then pOH is equal to the negative log of the hydroxide ion. So for this problem, it says, what's the pH of a 1.2 times 10 to the negative fourth molar sodium hydroxide solution? Okay, so we have our OH minus concentration here. We do not have the H3O plus, okay, because NaOH is a strong base. It gives OH minuses. So if we use pOH, write out our equation. pOH is equal to the negative log of the hydroxide. Plug in the concentration. We get 3.9 as our pOH. Then, if we subtract that value from 14, that will allow us to have our pH value, which is 10.1. Now, this one says that there is another way that you can calculate this. So if you would prefer to not use pOH, you can also use your kW expression. So kW, if you recall, is equal to the hydronium ion concentration times your hydroxide, and we always have kW as 1 times 10 to the negative 14th. So if we're solving for hydronium in order to find pH, and we were given our hydroxide, we can take kW divided by our hydroxide, and that will give us our H3O plus concentration, and then we could plug it into our pH equation, which is the negative log of the hydronium, and that would give us the same value. So you can either use kW or you could use pOH, and then you would still end up with the same result. Now, to find the pH of a weak acid, you can't just plug in a concentration straight into an equation the way, our pH equation, the way we can with strong bases. Strong bases can almost completely dissociate, so whatever the concentration is of the strong acid or base will be the concentration of the hydronium or the hydroxide. With weak acids or bases, you're going to have to make an extra step. So for a pH of a weak acid, you're going to use Ka, or your acid ionization constant, to solve for H3O+. So like in this one here, you've got HCN combining with water to make Cn- and H3O+. So we're going to put our Cn- ion times our H3O+ ion over our HCN. And again, water is excluded because it's a liquid. And then we will solve for our H3O+. Okay, this problem would give us values to be able to calculate our H3O+. And then once you have that, you could use your pH equation. Same type of thing for your weak bases. You can use your equilibrium expression to solve for OH minus. So aqueous products divided by aqueous reactants, you would solve for OH minus, and then you could either use Kw to find H3O plus, or you could use POH and subtract it from 14. An indicator is going to be a dye that changes colors in solutions of different pH. And there's all sorts of different indicators that can be used. There are actually a number of natural ones, like different types of plants. Red cabbage actually can be used as an acid-base indicator. Hydrangeas, if you have those flowers in your yard, that can tell you the pH of your soil. You also have different actual chemicals, like phenolphthalein is a very common one. It's normally clear, and when you add it to a base, it turns pink, and when you add it to an acid, it stays clear. Bromthymol blue, methyl orange, methyl red. There's a whole number of different indicators that you could use depending on what acids and bases you're using. Then there's also a pH meter I showed you in the picture earlier that gives you an actual digital readout. Then there's litmus paper, like red litmus turns blue when you put a base on it, and blue litmus turns red with an acid. Or there's just pH paper or hydrion paper that you put a sample of your solution on it and then compare it to the scale, and that'll tell you a number value of what the pH would be. The last thing we're going to mention here is a buffer. Now, a buffer is a solution that is going to resist changes in pH. So like in our blood, the liquid portion of our blood needs to stay between 7.35 and 7.45 pH. So it's a very limited range. And a buffer is composed of a weak acid. In our blood, it's carbonic acid, H2CO3, and its conjugate base in approximately equal amounts. So it actually will follow Le Chatelier's principle to counteract the effect of an acid or base being added to that system. So if you get too much acid in your system, it will shift to relieve that stress, get rid of the excess acid. If you get too much base, it'll do the same type of thing but shift the opposite way. It will try to get rid of that extra base and get back to equilibrium.